Hello everyone. This will act as our practice video. So I'm actually going to break this up into 3 videos. So the first video here is going to be on resonance. Our second video is going to be for the 1-2 versus the 1-4 addition reactions. And then the third video for this series of practice will be the Diels-Alder reaction. Alright, so in getting started here, resonance practice. It just wants us to draw the number of indicated resonance structures for each compound or ion. All right, now I feel that this is very necessary for you to actually kind of understand the intermediate steps for 1-2, 1-4 additions, as well as Diels-Alder. Well, not as much Diels-Alder, but then when we start talking about electrophilic aromatic substitution, there's a lot of resonance in those intermediates. So this practice is necessary for that, right? And let's be honest, students tend to struggle a lot with resonance. So first off, here we have ourselves a cation. Right now, remember, electrons move in a very certain way, right? They move from an electron-rich area to an electron-poor area, and you want to take the simplest step you can. All right, so for instance, if you notice this overall structure right here, the double bond to the single bond there, at the end of our single bond here we have a plus charge. So that carbon is an electron-poor carbon. So we would expect then the double bond here to shift there. So out of the ring towards this positive charge, right? So you're moving from electron rich with pi electrons towards electron poor. Now what does that do? So the first structure we would get would be, we didn't touch that pi bond, so we'll leave it there. And then now this CH2 group that came off, it now has the double bond. And so because of that, what has happened? Now you have this carbon here no longer has that pi bond, so it is what became positive. So this would be your simplest step in forming a resonance structure. Now, we don't want to go backwards, so let's just keep going in the same general direction. All right, so in this case, now the simplest step we could have is, you notice I said double, single, and then a positive charge at the end of the single bond. Well, look at that. Double, so double, single, positive charge at the end of that single bond. So you can have just another one of these pi bond, this pi bond now, shifting up towards that positive charge. And that would give us our second of the desirable resonance structures. So now the double bond is going to be here. So we want to put it right there. And our plus charge should be at this carbon, right? Because it lost the pi bond. Like so. All right. Now for this guy here in drawing the resonance structures, you have a few options. One thing, you have a highly polarized bond here. So you got a double bond between a carbon and an oxygen, and it is polarized. So technically there is a resonance structure that looks like this, where it just moves up. So I won't change any of those pi bonds. Now because of that, there were 2 lone pairs there originally. Now there's going to be 3. 1, 2, 3, 4, 5, 6. So there's our 3 lone pair. And that gives our oxygen a -1 formal charge. And then our carbon lost that pi bond, right? So it lost some electron density there, so it's got a positive charge. Now, this is not really the one that it's specifying in terms of give us a resonance structure. The 3 that it's looking for would actually be, because this, right, having a positive bound to a negative charge, that's not really a stable resonance structure. But to kind of help show like why this is happening, I felt it necessary to show this. So technically, we could say this is a resonance structure, but it's not one of the more stable ones. What would happen instead, you notice, right, double bond, single bond, positive charge. Double bond, single bond, positive charge. So that bond, so now the pi bond can move out of the ring towards that positive carbon. All right, and then you're going to get, all right, the double bond now on the outside here, and this carbon lost the pi bond, so it's got a positive charge there. All right, from there, All right, we could see yet again the same thing, right? Double bond, single bond, positive charge, right? So double bond, single bond, positive charge. So we would expect this pi bond to move up like that. I'm going to move this page over. All right, and so now that carbon, which is this one, right, it lost the pi bond, so now it should have a positive charge here. All right, and then the last of the three that it's actually wanting, so it's really this one, so it's these two, and then I'm gonna shoot it up here so you can see it, so I don't bleed into the next question. But you could see double bond, single bond, positive charge. So you would expect that pi bond to shift that way. And so you're going to have a double bond here, double bond there. Keep our negative oxygen up there, all right? So there's where all the pi bonds would have went based off that movement. So those two originally didn't move. But notice this carbon here had the pi bond, now it doesn't. So it should have a positive charge now. So these are the three resonance structures you're looking for. Sorry, if you don't know anything about Star Wars, you probably don't get that reference. Anyway, so next up, here we have something that's neutral like the one above. Now, the interesting thing here is you've got to remember, like for this nitrogen to be neutral, it's showing that it has 3 bonds. But with those 3 bonds, to be neutral, nitrogen also has to have this lone pair. Okay, so there is no formal charge stated. That's what I'm trying to get at with neutral. Now, the thing that can happen here, and this becomes very relevant when we start talking about electrophilic aromatic substitutions, is that this lone pair can actually donate, right? And we'll see that with oxygens as well. So in this case, this lone pair can actually move here to where it's forming a double bond between this nitrogen and this carbon of the ring. Now what's going to wind up happening, this carbon already had 4 bonds, so that means this pi bond has to shift out somewhere. So you're going to do the simplest step possible. So we're actually going to move those electrons from the pi bond just onto that corner carbon. All right, so you notice what tends to be happening. Pi bonds can either move to make other pi bonds, or now you can see lone pairs can move in and then push pi bonds out and create new lone pairs. So the resonance structure we would see here for this move, keep those 2 pi bonds where they were. Now you're going to have a double bond here with the nitrogen. And because this nitrogen no longer has 3 bonds in a lone pair, it's got 4 bonds, it will have a plus charge. And then here the pi bond moved out in the form of a lone pair, and this carbon should get a negative charge, right? And so what you should also be noticing is that in your resonance structures, your overall charge of the molecule should stay the same. So here it was neutral, there it was neutral, right? So here you don't see any formal charges at all, so it's all neutral. But here it's +1, -1, and that is neutral. All right, so what you would expect is pretty much a series of these same steps. Lone pair creates a pi bond, and then a pi bond gets forced out as a lone pair. So here's the lone pair, and so going in this kind of counterclockwise fashion, this lone pair is now creating a pi bond here, which would then force this pi bond out to create a lone pair. Sorry, that ring, it just couldn't, it lost its integrity, I guess. All right, then that pi bond stayed there. All right. Oop, and I forgot my negative charge here. Okay. All right. And then for the third one, it's very consistent, right? So what did you see? Lone pair creates a pi bond gets pushed out to make a new lone pair. All right. Lone pair creates a pi bond, right, that we saw here. And then pi bond gets pushed out to create a lone pair, which we saw here. And so same thing's going to happen. Lone pair is going to create a pi bond gets pushed out to create a lone pair. There you go. I gave that ring back its structural integrity, so it's not lopsided looking there anymore. All right. So let's see. The pi bond down here didn't move. So this creates a pi bond right here, and then this creates a pi bond. The pi bond moves out as a lone pair there. Okay, so those are the three resonance structures it's looking for. Okay, and it's going to be very important that you remember this type of resonance when we talk about electrophilic aromatic substitutions, which take place after Diels-Alder. Okay, all right. Next up, we have this ether alkene functional group. So here's your ether, there's your alkene, and so very similar to what we saw with the nitrogen's lone pair. Oxygen here has two lone pairs. And one of its lone pairs can actually move this way in the direction of the double bond and then force this double bond out, or force the pi bond out as a lone pair. So the only real resonance structure you see here would be this. Oh, and I forgot, you got to have a positive charge on this oxygen here. Okay. All right. Next up, the resonance structure we would expect for this one. So electronegativity can sometimes play an effect here, and so you have to think about. You don't expect this oxygen does have two lone pairs, but you don't expect it to move down here because that double bond, it can't, even if it moves this way, you're going to overload this carbon, so it's going to have more than 8 electrons. So the only real option you have here is to force this pi bond here to move it there between these two carbons, and then push this pi bond up. All right, and so what winds up happening, what does that mean? That means now, let me draw that backbone. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. All right, so you're going to have an oxygen-carbon single bond, no longer a double bond, and now that oxygen should have 1, 2, 3 lone pairs on it and a negative charge because of that. All right, now also we move this pi bond to right here, so you'll get this, and then that carbon gets a plus charge, like so. Okay. All right, and notice it was neutral overall. +1, -1, neutral overall. It's all good. All right. Next up on our resonance extravaganza. So what does it mean for this oxygen to have a negative charge? Right here, it's got 3 lone pairs. So we should see 1, 2, and then I'll put the third one right there. All right. So the only real resonance structure you have here, you've got a double bond, single bond, and a charge. So your resonance structure is going to be between these 3 atoms here. And what you would expect is, remember, you move from electron rich to electron poor, more or less. And so you can see negative, right, means that's electron rich. So one of your lone pairs is going to shift to right here. And then what's that going to do? Well, the carbon right now has 5 bonds on it. That's 10 electrons. You can't have that. So the pi bond is going to move up to right here. Okay. And what are we looking at? So we got a ring. We're going to see oxygen, oxygen. So now the one up here should remain a single bond, but now this one down here is going to have the double. So it'll have 2 lone pairs and a double bond, and now this one will have a single bond and 3 lone pairs to give us that negative charge up there. All right. Next up, 4 resonance structures on this one. What a beast. All right, so here's the deal. This is going to work in a couple of... This is actually going to go in 2 separate directions. So you have one set of resonance structures where one of the 2 lone pairs on this oxygen can move this way, right, to then push up the pi bond there, right? So there's that. This would be one of the 4. So the pi bonds in the ring didn't do anything, and you're going to get an oxygen that's got that double bond, oxygen with the single bond. So it kept 1 lone pair. Now that one has 3. 1, 2, 3. So you get a negative charge on that oxygen, a positive charge on that oxygen. All right. So that's one direction that this lone pair could move. Okay. And to give us one of the 4 resonance structures. But this lone pair could even move in this direction as well. Because you notice, right? Lone pair, single bond, double bond. Right? It was the same thing here. Lone pair, single bond, double bond. So, if say the, let me redraw it. So if instead, so this is just that, I just redrew it. All right, so now instead, if the lone pair up here moved this way towards the ring, boop, to create the pi bond on that side, what would that do? Something very similar to what happened up here with the nitrogen, right? It's going to force lone pairs on these corner carbons, so it'll put a lone pair right there on that carbon. So I'm going to label that as carbon number 1. Right, or resonance structure number 1, and then so our second resonance structure would be that. So this would be resonance structure number 2. All right, then for 3, right? So remember, lone pair creates a pi bond kicks out and makes a lone pair. So lone pair will create a pi bond. That forces a pi bond out to create a lone pair here. So then our third resonance structure, here, let me go up that way, would be double bond here, double bond here, double bond here. So many double bonds. All right, so now this carbon is what has the lone pair, which is that one right there. And that gives us our negative charge. Okay, so this would be resonance structure number 3. And then our last and final one, same move as what we saw here, here and here, here and here, right? So the lone pair is going to move this way, create a pi bond, and that'll force the pi bond out onto that corner carbon to give us our final resonance structure. So let's see, pi bond there, pi bond there, pi bond there, and then lone pair on this corner. All right, and so that would be resonance structure number 4. All right, see if I can get it to where you can see all 4 of them at the same time. There you go. So there you go. Try to block it in so you can see it a little bit better. All right, and then lastly, our last resonance practice gives us a positive charge. All right, so what do you notice? We have a double bond, single bond, positive charge. And so what we're going to see, pi bond will move up there, right? Electron rich moves towards electron poor. And so because of that, hydrogen, bromine, we didn't touch this pi bond, so now the pi bond is moved up here on the side. And then what happened? This carbon lost the pi bond, so it should get the positive charge. All right. And then our second resonance structure is very similar, right? Pi bond's going to move this way towards the positive charge. Let me put that hydrogen and bromine on there. Boom, boom. And so now our positive charge would go, right? This carbon had the pi bond, now it doesn't, so it's got the positive charge. All right. So in closing, there's your resonance practice. Make sure that you are comfortable with these. All right. See you later, Chem Minions.